Let's take a look at Chapter 7-4, where we're going to be exploring more about similarities, specifically in right triangles. And what happens is if we take a right triangle and we draw in the altitude, which remember is like the height of a triangle, specifically drawing in the altitude that goes from the right angle to 90 degrees through the hypotenuse, we divide our triangle up into 3 triangles. We have our original triangle, which we can see here is triangle ACB, and then we've also created 2 other triangles. The smallest triangle here, triangle ADB, which they've redrawn here for us, and the medium-sized triangle in green, triangle CDB. And what's interesting about that specific way of drawing in the altitude is that we've taken one triangle and created 3 triangles that are all similar. So they're similar. If you pick out any 2, they're similar. They're all similar to each other, meaning all their angles are congruent and all the sides are proportional. Now, it can be tricky to identify these triangles and to see how we have similar triangles if you just leave it as the original figure with the altitude drawn in. Notice though here how they take that original figure and they break it up and redraw the small and the medium-sized triangle. They not only redraw them outside of the triangle, but they draw them having the same orientation, meaning they're facing the same direction. They look like they're similar. And that's what we're going to practice doing with our first couple examples here, is taking a right triangle, drawing in the hypotenuse that goes from the right angle, drawing in the altitude that goes from the right angle to the hypotenuse, and then re-sketching the 2 triangles we've created to have the same orientation or face the same way and identify our similarity statements. So that's what we're asked to do. Number 1, what is the similarity statement that can be written relating the 3 triangles in this diagram? So I'm going to redraw all of my triangles, and I'm going to start with my largest triangle. And bear with me as I do my highlighting here. I'm going to draw the largest triangle in orange, and I'm going to let that set my orientation, meaning my hypotenuse kind of faces up and to the left. I like to draw my right angle. My right angle in the large triangle is Y. My short side is XY. My long side is YZ. Those are the questions I ask myself so that I make sure I'm putting the vertices in the right location. Now I'm going to take a look at the medium-sized triangle. I'm going to outline that here in green, and you can do the medium or the small next. It doesn't matter which order you choose. But I'm going to make it look like my triangle here in orange. I might make it a little bit smaller, and honestly, if you make them the same size, that's not as big of a deal. So it's a little bit smaller, but notice how it has that same orientation. Again, the hypotenuse is facing up and to the left. So if we look over here at our original figure, it's kind of like I spun my triangle here in green counterclockwise, maybe about 80 degrees or so. And again, I like to start by identifying my right angle. And in the green triangle, the right angle happens at vertice W. And my short side, which would be the right side here, corresponds to WY, which means Y is going to be my top vertex. And my long side is side WZ, so Z is going to be this remaining vertex. And always double check with your hypotenuse. In the triangle I just drew, my hypotenuse is side ZY. Remember, hypotenuse is our longest side, opposite the right angle. And if I look at the original triangle, ZY is in fact the hypotenuse, so that's good. And let's do the last one. I'm going to do that here in blue. It's going to be my smallest triangle. But again, I'm going to start by sketching it so it has the same orientation. It's facing the same way. I'm going to sketch in my right angle first. The right angle again happens at W. Now my short side is kind of this top side in the original figure, and that's WX. And the long side is WY. Again, double check that your hypotenuses match. My hypotenuse in my redrawn triangle is YZ. That does match what my hypotenuse shows in the original figure. So by resketching these, I'm making it easier for myself to write my similarity statement. Because remember from section 2 how important it is when you're writing your similarity statement that corresponding angles and corresponding sides match up in your that you write your similarity statement in corresponding parts order, so your corresponding angles match. So I'm going to write my similarity statement. You can do this a variety of ways, but however you start your first triangle, the other should follow. So I'm going to start my first triangle, and I'm going to call it XYZ. And one thing I like to make note of is how I came up with that order. X to Y is the short side, Y to Z is the long side. So I went short side, long side. I'm going to say that's similar to triangle. I'm looking at the green triangle now, the middle-sized triangle. And again, I want to go short side to long side. So I'm going to go Y to W and then W to Z, or Y, W, Z. And it's similar to, we're going to have a 3 triangle similarity statement here. And again, be consistent. Short side to long side would give me triangle X, W, Y. So see how much easier that is than just taking that original figure and trying to figure out which sides correspond by just taking a few seconds to redraw them and make sure that you list your vertices in the right order will make your corresponding parts order much simpler. Let's try one more. We've got 2 parts here. The first part asks us to write our similarity statement relating these 3 triangles. Again, we've got a right triangle with the altitude sketched in. And then the second part I'm going to look at for some different proportions. So let's just start with the redrawing portion first. Again, I'm going to do that first triangle first. I'll do it here in pink, and I'm going to leave the orientation the way it is. I'm going to leave it with the hypotenuse facing straight up. So I've got my triangle. My short side is on the left. My long side is up the right. My right angle happens at vertex P. My short side is QP, my long side is PR. So in pink there is my large right triangle. I'll do the medium one again, and I'll do that here in green next. But instead of doing that, the orientation it's shown with the hypotenuse facing down and to the right, we want the hypotenuse facing straight up so it matches that first triangle we drew. Short leg along the left, long leg along the right, and my right angle at the bottom. So in the green triangle, my right angle is vertex S, and my short leg is side SP. So SP needs to be along the left. My long leg is side SR. And again, do that double check. In my redrawn triangle, my hypotenuse happens at PR, and that is the hypotenuse of the green triangle from the original drawing. And the last one, let's do a light blue here. We're going to do the little triangle over here on the left. And start by sketching with the hypotenuse up. Little leg to the left, long leg to the right. Start by sketching in that right angle. Again, my right angle happens at vertex S. My short leg is side SQ, and my long leg is side SP. And then double check, is your hypotenuse on the original triangle QP? Well, it definitely is, so we've kind of verified that I've got my vertices in the right order there. So to write my similarity statement, again, you don't have to start with the large triangle, but I'm going to for consistency. And I'm going to start with, I'm going to call it triangle QPR. So Q to P is the short side, P to R is the long side. So that's going to be the same order I'm going to want to go for all 3. So the middle triangle, be short side to long side, is similar to triangle P, SR. And my last side, short side to long side, gives me Q, SP. That's my similarity statement. All of this was part A. Part B asks us, from the similarity statement part A, write 2 different proportions using the ratio SR over SP. So I know I need to start with SR over SP. And if you notice, SR shows up here, and SP shows up here. So if we want to look at my triangle, SR is this side here, over SP is this side here. So it's like taking the long leg of my middle triangle over the long leg of my short triangle. So knowing my similarity properties tells me that that ratio should be the same as the ratio of, I'll grab a new color here, let's do red, of the short leg over the short leg. So PS over QS. And again, we want to do another one of that same one. So SR over SP is also the hypotenuse over the hypotenuse. So PR over QP. So 2 different ratios we can write there. That's the first part, and we're going to use that as we continue down. Now we're going to kind of have this little middle section here talking about geometric mean, and then our last part is going to be relating those similar triangles in a right triangle with the geometric mean. And when we're writing proportions in which the means are equal, meaning the bottom number of the first fraction and the top number of the second fraction, we call that, for any of the two positive numbers, a and b, the geometric mean of a and b is the positive number x, such that a over x is equal to x over b. So that's kind of a lot of words. What does that mean? Well, here we're asked to find what is the geometric mean of 6 and 15. So if we want to look at this definition up above, 6 would be my a and 15 would be my b. So to find the geometric mean, we're going to take 6 over x, set that equal to x over 15. Now I've got a proportion, and we can cross multiply to solve for x. Cross multiply 6 times 15 is 90. X times x is x squared. So 90 is equal to x squared. We want to get x by itself, so we're going to square root both sides. I'm just going to flip my order here. X is equal to the square root of 90. Now 90 is not a perfect square. In this chapter and from here on out, when we're working with square roots, we always want to write them in what we call simplest radical form, which is hopefully something you've seen before in algebra. If you have no idea what I'm talking about, let me know and I'll gladly go over some review on how to write in simplest radical form. But what that means is that we want to take out any perfect squares that are a factor of our value 90. And 9 is a perfect square and 9 is a factor of 90. So I can rewrite square root of 90 as a square root of 9 times 10, because 9 times 10 gives me 90, and 9 is a perfect square. And then we have these properties of radicals that says if you're multiplying underneath the radical, you could actually split that up into two separate radicals, square root of 9 times the square root of 10, and the square root of 9 is actually 3, so we're left with 3 times the square root of 10. That's simplest radical form. So the geometric mean of 6 and 15 is 3 root 10. Or 3 square root of 10. That's what your homework will be looking for. Again, if you need help with that, let me know. We'll do one more example where we practice simplest radical form. So again, we're asked to find the geometric mean. So 4 over x equals x over 18. And you could certainly flip those numbers around. Remember everything we talked about from section 1 with proportions, how we can write them different ways, but they still mean the same thing. 4 times 18 is 72. So we get x squared equals 72. Square root both sides. X is equal to the square root of 72. Again, 72 is not a perfect square, but it does have a perfect square that is a factor of it, and that's the value 36. So I can rewrite this as the square root of 36 times 2, because 36 times 2 is 72, and 36 is that perfect square I'm looking for. Break up those radicals, square root of 36 times square root of 2, and simplify. Square root of 36 is 6, so 6 root 2 is the geometric mean of 4 and 18. So a little bit of a side note, not directly related right away, but this next slide here, this next picture here is going to show us why we care about that. So if we're looking at those 3 triangles created by drawing in the altitude of a right triangle, we can set up our proportion, since our triangles are similar, that says the short leg of this triangle here in blue over the short leg of the triangle in green is equal to the long leg of the triangle in blue over the long leg of the triangle in green. Notice here that we repeated the short leg in one triangle is the long leg in the other triangle. So instead of using short leg, long leg, we could say QS over SP equals SP over SR. Notice SP shows up on both top and bottom, meaning SP is a geometric mean of SQ and SR. So we can use that to come up with some theorems about these right triangles when we draw in the altitude and create 3 similar triangles. First one says that the length of the altitude to the hypotenuse of a right triangle is the geometric means of the lengths of the segments of the hypotenuse. That's what we just looked at. So we can look at that as the short side over the long side equals short side over the long side of the small triangle equal to the large triangle. And when in this case, we have values for all that. So 2 over 4 equals 4 over 8. We're going to practice doing that when one of those is a variable, and we can set up that geometric mean to solve. Now, we have other ways that we can look at the same type of process. And this is our next theorem, or corollary 2 to theorem 7-3, and that says that the altitude of the hypotenuse of a right triangle, which is what just drawing in that altitude, separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse, and the length of the segment of the hypotenuse adjacent to the leg. So it's a lot of words. That itself is very hard to understand. But here's what I recommend for this. A, use the picture, or the example here. 4, which is the hypotenuse of my large triangle, over 2, which is the short side of my large triangle. So hypotenuse over short side equals, now we picked a different triangle, the small triangle, and we set up the same proportion, or the same ratio. Hypotenuse, which is 2, over the short side, which is 1. So we're still using those same properties of triangles that we've been working with in our similar triangles. We just have a different way of looking at it. Now, this I added because I think it's very helpful. Kind of shorthands those two corollaries that we just looked at into, I think, a little bit easier way of reading it, and I'm using variables instead of actual numbers. So at first, this is probably going to be pretty overwhelming. Take your time at it, go slow. You might make some mistakes, ask questions if you have them, but really use what I just circled here in red. If you have these, this little piece of your notes handy, that will help you through all of your homework questions. So let's go ahead and try this. We've got a triangle here, and we're asked to find the values of x and y. Now I'm actually going to find y first, because that uses corollary 1. And if we look here, corollary 1 says if you take S1, which is like the leg of one of your triangles, over that altitude, it's equal to the altitude over the leg of the other triangle. More clearly, looking at this triangle here, the long side, or the altitude, y, over the short side, 4, if I'm looking at the small triangle, y over 4, long side over short side, equals, let's look at the big triangle, or excuse me, the medium triangle. And again, we want to do long side over short side. Long side is 12, over short side is y. Okay? Or use this shorthand up here from corollary 1. A piece of your hypotenuse of the large triangle over the altitude equals the altitude over the other piece of your triangle. Two different ways of saying the same thing. Now once we've got your proportions set up, we can use cross multiplying to solve. Y times y is y squared. 4 times 12 is 48. Square root both sides to get y by itself, so y is equal to square root of 48. And again, 48 is not a perfect square, but we do have a factor that is a perfect square of 48, and that's the value 4, so we can rewrite this as square root of 4 times the square root of 12, which gives us 2 times the square root of 12. So y has a value of 2 root 12. Now let's take a look at x for a second. If we look at the big triangle, the largest triangle here, x is the short side. And I can take the short side over the hypotenuse, so the short side here, hypotenuse is here. And my hypotenuse has a length of 12 plus 4. Just because the way they've labeled it is that they've labeled it in 2 chunks. We want to add those 2 chunks to get the length of the hypotenuse. So short side over the hypotenuse equals, now let's take a look at the small triangle here in purple. The short side is this side 4, so we want short side over hypotenuse is this side x here. And you can see that in this kind of shorthand up here if you look at corollary 2. So now cross multiply to solve. Let's pick a new color. X times x is x squared. 12 plus 4 is 16. 16 times 4 is 64. So x squared is equal to 64. So x is equal to the square root of 64. 64 is a perfect square, so I get a nice little number of 8. So I know that's kind of a lot to take in. I think this section is one of the more challenging ones at first, but once you get it, it should kind of fall into place. Let's try another example. Same type of situation. I've got a right triangle. I've drawn in that altitude that goes from the right angle to the hypotenuse, and I want to find x and y. Again, I'm going to start with y first. And if you want to look at it as the kind of the smaller triangle on the left, and then the medium-sized triangle on the right. In this case, I'm going to say that y is the long leg of my small triangle. So I'm going to say long leg over the short leg is the 4. So if this triangle on the left, the long leg is y, the short leg is 4, equals, if I look at the triangle on the right, my long leg is the 5 over my short leg is the y. Now, cross multiply to solve. Y times y is y squared. 4 times 5 is 20. Square root both sides. Y equals the square root of 20. And again, always factor out any perfect squares. 4 is a factor of 20, and that's a perfect square. So I'm going to rewrite this as the square root of 4 times the square root of 5. Square root of 4 is 2. So y is equal to 2 root 5. For x, we're going to look at it the same type of way. We want to look at the little triangle on the left first. X is my hypotenuse, so I can take my hypotenuse over my short leg, x over 4, equals, now let's look at the big leg, or excuse me, the big triangle. We want to start with the hypotenuse, which is 4 plus 5, or 9, over the short leg, which is x. Again, cross multiply to solve. X times x is x squared. 9 times 4 is 36. Get x by itself by square rooting both sides. X is equal to the square root of 36. Oops, try that again. Which is 6. So x is 6, y is 2 root 5. All right, we got just one more example to look at here. We're looking to find a distance. It says you are preparing for a robotics competition using the setup shown here. From points A, B, and points A, B, and C are located so that AB is 20 inches, and that's labeled on here. AB is perpendicular to BC, and let's see, where was I? Point D is located on AC, so that BD is perpendicular to AC, and DC is 9 inches. You program the robot to move from A to D and to pick up the plastic bottle at D. How far does the robot travel from A to D? So I'm looking for this distance here, x, A to D. What they've set up for us here is one large right triangle, that's triangle ABC, and I've got the altitude drawn in from the right angle to the hypotenuse, that's side BD, splitting my triangle into 3 right triangles. So I want to set up here some proportions so that I can find that distance from A to D. So to do that, I'm going to start by taking the hypotenuse of my big triangle. So the big triangle is triangle ABC, and the hypotenuse is this length from A to C. So I don't know exactly what that is, but I know it has to be equal to 9 plus x, whatever 9 is, or excuse me, whatever x is. So I take that hypotenuse, 9 plus x, and I'm going to put it over my long side. My long side is 20. So now I've got to take a different triangle and set up the same type of thing, hypotenuse over long side. Well, if I look at this triangle BDA here, kind of this right-hand triangle, my hypotenuse is 20, over my long side is x. So now I've got one equation with one variable. I can use cross multiplication to solve for x. Now what's really important here, and we've practiced this in section 1, is that we have these implied parentheses here. So when we cross multiply, we get x times this quantity 9 plus x equals 20 times 20. Now on the left side, I'm going to distribute the x, which gives me 9x plus x squared, and the right side 20 times 20 is 400. Now notice here, anytime that you have an x squared term, an x term, and a constant, or a term that doesn't have an x, we're going to have to use factoring or quadratic formula, but in this case factoring to solve. And in order to solve using factoring, I need to set this up in standard form, meaning my x squared term is first, my x term is second, and my constant is third. And to do that, I need to subtract this 400. I need to set it equal to 0. So I'm going to subtract 400 from both sides, and in that same step, I'm going to kind of rewrite the left-hand side. So I'm starting with x squared, then I'm adding 9x, then I'm subtracting 400, and I'm setting that equal to 0. I know we touched on this a couple weeks ago, and some of you, this seemed like it was brand new to you. Again, I'm less concerned with that you know exactly how to solve this, as I'm more concerned with that you know those properties of the right triangle similarities. But if you do need help with this, please just holler. I'll be happy to go over it with you. Now, when we're solving quadratics, if I'm multiplying by 1 out front, if there's no number in front of the x squared, I can do this little trick where I look at my c value, or my constant value, and I say, hey, is there any two numbers that multiply to give me negative 400 and add to give me 9? And sometimes, especially with a large number like negative 400, we're going to have to do a little bit of guess and check. But if we pick the numbers negative 16 and 25, if I multiply negative 16 and 25, I get negative 400. If I add negative 16 and 25, I get positive 9. So those are two values I'm going to use when I factor. And to factor, I kind of just have two parentheses like this, and again, it's still equal to 0. I have an x as my first term in both, and I use these two values I found that have the same sum, or that have a sum to get me my middle number and have a product to get me my last number. So x minus 16 and x plus 25. And it doesn't matter which order you set them in. Now we're almost done here. The last thing we need to do is we need to say, hey, I actually need to know what x is. Well, anytime you've got two numbers multiplied by each other and you get a product of 0, or you get an answer of 0, one of those numbers has to be equal to 0, and that's called the zero product property. So then we say x minus 16 has to equal 0, or x plus 25 has to equal 0. Set up two different equations and solve for x. On the first equation, to get x by itself, I'm going to add 16 to both sides. So I get x equals 16. In the second equation, I'm going to subtract 25 from both sides to get x by itself, and I get x equals negative 25. Now let's go back up to our problem here quickly. X is this distance here between A and D. X is the distance that this robot has to travel. So in this case, the case of this problem, it doesn't make sense to have a negative distance. My robot isn't going to travel negative 25, so we're actually going to not use that as an answer. We're going to just take the positive value, x equals 16. So again, don't get hung up on the factoring and zero product property. If you need help, I'll definitely go over that with you. But for the sake of this problem, I'm really most concerned with can you set up those proportions using the right triangle similarity? If you need any help, don't be afraid to ask.